Hello, welcome to Lab 2, presentation, Lines of Charge by me, Pratham Galar. So, quick introduction, the lab goals and purpose. So, last week we did the electric tape lab, and we modeled the charges computationally as point charges. And this week we're going to change that and model them as lines of charge instead of those point charges. We also want to find the magnitudes of the gravitational electric forces that are applied on tape B, which is this red tape up here. And we want to find the magnitude of the charge itself on the tapes, because the one we found last week was, it was for point charges. The results, real quick overview. The charge of the tape I found to be 1.456 times 10 to the negative 8 coulombs. The force of gravity was 1.69 times 10 to the negative 3 newtons. And the electrostatic force was 1.4 times 10 to the negative 3 newtons. So some physics in the background for this introduction. We're still going to be using these three laws. We have Coulomb's law, Newton's second law of motion, and the gravitational force equation. Since we know there's no acceleration, the net force is zero, which means the force due to gravity and the force due to Coulomb's law has to be equal. Setting these two equal to each other, we can solve for Q. But it doesn't work that way. Now we have to consider that they're lines. So we're going to use this special formula, which is for the electric field of a line, which we did derive in class. And then alongside the alternative equation for Coulomb's law, or not Coulomb's law, but just electric force, which is F equals QE. So by using this E, we can solve for F and then set it equal to the gravitational force, which is down here. So quick calculations, we start with FE, as I mentioned previously, and this is just using the E times Q. Then we know FE has to equal FG because the net force is zero, because acceleration is zero. So we get to mg equals kq squared over d square root of d squared plus l squared over 4. And then plug in our numbers and we get q. So rearrange, solve for q, and then plug in the numbers. We get q equals 1.456 times 10 to the negative 8 coulombs, which is what we use in the code. So quick systems, surroundings, initial conditions. This is mainly the same from last week. The system is tape B. The surroundings are tape A. Initial conditions, the length of the tape is 0.172 meters. The width is 0.019 meters. The mass is 1.72 times 10 to the negative 4th kilograms. The initial charge is that they're both neutral, they're both zero. And the distance between them, this distance d, is 0.0125 meters. So last week we used a point charge, and we got the magnitude of charge to be 5.629 times 10 to the negative 9th. But let's see if we can model it a bit better. Let's go into this week's line charge. So this is the code. We start with defining an electric field, defining a line charge, and this creates the setup. And then we define the vectors, we calculate the electric field, calculate the forces, and then display them down here with these three arrows, these two arrows. And then we print out the values, which you can see now. So magnitude of electric force, magnitude of gravitational force, and then the estimated net charge, which is we calculated using the formulas. So comparisons between this week and last week. The similarities is that both models show how the collection of charges interact with each other and the calculated forces that are applied on tape B. Both models also needed to assume that the tapes had equal charges spread evenly through them and that the effects of air resistance are ignored. We will get to assumptions on the next slide. The differences is that the lines of charge model, which was this week, resulted in a higher magnitude of charge on the tapes than the point charge model did last week. So this shows us that the point charge model needed to make assumptions that the tapes could be represented with point charges, which this model that we did this week did not have to. So let's go to assumptions. Air resistance. The tapes aren't perfectly aerodynamic and there will be force of drag due to air resistance, but we're ignoring that for the sake of this computational model. The tapes have the same charge. We're assuming that they have the same charge for the purpose of the calculations and equations, but in reality they might not have the same charge. Charge distribution. We're assuming that they're distributed evenly for the purpose of having the line. We know that each dq in a dl, infinitesimally small length, has the same charge. And then the tapes are modeled by lines of charges. So this is better than last model, but we might still be oversimplifying the rectangular shaped tape into a simple line. And now sources of error. One is loss of charge. There's a chance that the tape, when it was in contact with humans or the boxes, that it lost some charge and resulted in a situation where the charge is fluctuating during the experiment. The weight of tape was also estimated. It wasn't measured by scale, so the gravitational force itself might be wrong. And then there are other general human causes for error, such as the discrepancy between the values of the two forces. What if and why questions. What if we model the tapes as single point charges? How does the value of charge change? Well, we did this last week. And we can see that it went down from 1.456 times negative 8 coulombs to 5.629 times 10 to the negative 9 coulombs, which is a pretty significant change, which means there's a major difference between the representations of line charges and point charges. Question: why do these estimates differ? Which value is more likely to be closer to the actual value? The estimates differ because the electric field works differently depending on the model we take. If we model the tapes as lines, it creates a more holistic view of the electric field and superposes the electric field created by every little dq on the line.